Okay, so I guess I remember talking about diazomethane. Hmm? All right, so if we were on slide 24, um, so we had made it to the diazomethane part as kind of a different way to make an ester. So we were like, we made it to that middle structure on slide 24. Let me share my slides, a share in here. Hey Zoom, come back. Oh. Of course, now my internet connection's unstable. Thank you, Coastal. Thank you very much. Let me do this. Share this, and then that lets me share this easier. Oops. What's that? Okay, now we can do. All right. So we were here, right? So um, H2 and catalytic palladium. Here they're using palladium hydroxide, just another palladium source that removes the benzyl group. So that removes this protected group to give us an alcohol here. Then DMP oxidizes that to an aldehyde. This is another bleach oxidation, which turns an aldehyde into a carboxylic acid. This reagent here turns that acid into an acid chloride. And then they add this phosphonate ester to that acid chloride to give the Horner-Wessel-Emmons reagent. And it's got the fluorines on it, so it's going to it's going to prefer to do the cis double bond when they do the reaction. So next step, they take their Horner-Wessel-Emmons reagent, they take this aldehyde that they made previously, and they do the Horner-Wessel-Emmons reaction. So they use sodium hydride as the base, and that gives a cis double bond, and they get a 10-to-1 ratio of E to Z. So that was why they approached this way, is they felt that the Wittig reagents would not always give high Z selectivity, so they decided to use a Horner-Wessel-Emmons reagent to get this high 10-to-1 selectivity. They use DDQ, which is an oxidant, which specifically will take off this PMB is paramethoxybenzyl. We'll take that group off, and then they add this carbamate here. K-selectride is a big bulky hydride source, and so that's to reduce this ketone to an aldehyde, to an alcohol. And then they use HF, and HF does two things here. It's removing these two TBS groups, I guess three things. Removes these two TBS groups. It's acidic, so it also will open up this acetal to give these alcohols. And then you've got 1, 2, 3, 4, 5, 6. So this alcohol will then close onto this ester and makes this ring here. So that all happens with this step, this HF and pyridine step. You're removing your TBS groups, which I didn't take off. Way to go. Removes all those TBS groups that shouldn't be there anymore. And then gives you, we're going to fix that real quick. Yeah, come back. 1 second. I swear I kind of proofread these before I come to class. I swear, I swear. Camera, are you going to work? There you go. All right, real quick, let me fix this. So remove those TBS groups, and you get this. Much better. Oops. I'll get better at doing this eventually, I swear. One day. All right. All right. So you end up with discodermalide. So I found another synthesis that uses a Horner-Roberts Emmons reagent in kind of an interesting way. That's making this molecule here. So they use this activated ester to make an amide. So that has their Horner-Roberts Emmons reagent on it. And then they make an amide on the other side. I guess those of you in biochem have heard about DCC. So here's DCC being used to activate an acid, add the amide, right? Des-Martin oxidizes that to an aldehyde. Now you have a Horner-Roberts Emmons reagent on one side and aldehyde on the other. And they are able to use zinc triflate and some additives and base. And then they have, again, they run this at a really low concentration, 5 nanomolar, because they're trying to get this end of this molecule to react with this aldehyde. And if they have it at a higher concentration, you run the risk of this just reacting with another molecule and basically dimerizing. So they run at a really low concentration so it can only kind of find another molecule of itself to react with. Right? And then that cyclizes to this. HBr removes this protecting group. So I should show you what a Bach group is. It's pretty common. So you'll see Bach groups a lot. There's no one here. So whenever you see N, say like R, H, and Bach, that is this. This is Bach. And Bach groups are not acid stable. So if you add acid to these, your Bach group comes off and you get your amine back and you generate CO2 and effectively tert-butyl cation. It gets grabbed by something, but you get tert-butyl and say X if you use like HX. So that is the what a Bach group is. So whenever you see that, it's a tert-butyl carbamate is Bach. Sharing the yes, I am. Okay. So then I had to go look this up. This is just a resin, kind of a basic resin to turn when you remove a Bach group, you make a salt a lot of times. So they had to remove the salt so then they could do a coupling. So basically this adds to this carbon, so this amine will add to this carbon, which then opens this up. Let me draw that. See what I'm talking about? All right, so you've got an amine, and you've got this weird cyclic structure. And this has an H on it. So this is going to add to this carbon. This is going to come up. All right, and you get, it's a really ugly 5-membered ring. I apologize to all 5-membered rings. I apologize to your people. Oh, here, O, H, N, H, R. And then this lone pair will come down, push that oxygen off. Well, it actually does this. You'll make CO2. So you end up making try to do this right. Oh, I missed the nitrogen. And H. So this nitrogen right here ends up being here. So it goes there to here and through. This nitrogen, this is NH, ends up there. So it's just a way to like kind of do a peptide coupling where instead of having to use something like DCC or another peptide coupling reagent, you've made something that is already an activated ester that you can have add to it. And then I do another addition with this isocyanate to install this group here. And then they remove the ester to make the acid. So just a couple examples of Horner-Wadsworth Emmons reagents in synthesis. I'm going through these slides too fast. I only have 13 slides left. I don't want to make more. I guess I was talking about the slides. Let's go back. So there we go. You added your amine to this. This opened. This is an isocyanate, OCN. And so here's the O, here's the C, here's the N from that reagent right here. So the nitrogen that you made when you opened this is right here. It adds to the C of the OCN, and then you add that group on. And then the lithium hydroxide just saponifies this ester and turns it into an acid. So that is that. So I had a couple more, what are they called? Methods to make double bonds I wanted to go over. And so they're a little bit more obscure, but they're still used somewhat regularly, or some version of them is used. In the first kind of example here is a Julia olefination. So the kind of big thing about a Julia olefination is you have some sulfoxide, or sorry, not sulfoxide, sulfone, S double bond O, that you're able to add to a ketone or aldehyde. You then take that alcohol that you generate and you react with an acid chloride, and then you do a reduction to give you the product. So let's kind of walk through all the steps here. All right, so we've got our, usually it's phenyl or some other aromatic group on the sulfur, right? And then you treat this with base of some sort, and that is going to remove the hydrogen from this carbon right here and make an anion. All right, now I've made an anion. This is kind of like an enolate, where you could draw a resonance structure, right, where these electrons would come up here onto the oxygen. Right, but nonetheless, right, so it acts, the reason I can deprotonate it is because it's beside this electron withdrawing group. But I can take my anion and I can add it to, I can add it to a ketone or aldehyde. Right, it's going to just add to the carbonyl carbon, push electrons up onto the oxygen. Right, and you're going to make effectively a tertiary alcohol, kind of my example I have here. Then you add some sort of acid chloride. Right. Try to make sure everything matches. Right, and then you're able to, and then, right, your O minus adds to the carbonyl carbon, comes up, electrons come down, and you kick up the chlorine. Right, and you get something that looks like this. Right, so now this is something that you can isolate. It's something you can work with. All right, and then depending on the mechanism, I've seen the mechanism written a couple of different ways. I think the most common way that this happens is when you do your reduction. There's usually a base present, and I'm gonna need more iPad screen. So I'm gonna redraw this real quick. I'm drawing a hydrogen. So the base in the reduction will come grab this hydrogen. This hydrogen is acidic, right? Again, because it's beside the electron withdrawing sulfone. And then those electrons will come down and push off the ester, the acetate. And then your reduction, usually do something like samarium iodide or sodium mercury amalgam. What this will do is one of those reagents removes the sulfone from the molecule and makes a vinyl radical. So what happens is this will removes this group right here. So we end up with a radical. Now, if you remember from Organic 1, when we talk about reducing alkynes with like sodium ammonia, you would make a vinyl radical, and that vinyl radical is able to change its orientation, right? It basically is able to invert. So in this case, our methyl group is able to flip from side to side. In the methyl group, this group here is going to end up on the side of the double bond that puts it beside the smallest of the two groups, R2 or R3. Right, so I make this vinyl radical that the group on that carbon can flip back and forth, and then eventually it ends up being on the side that basically leads to the least interactions, right? You're going to put that group beside the smallest thing possible so you don't have those two groups banging into each other. And then that reducing agent, let's say that R2 is the smaller group, that reducing agent, that reductant, will turn that radical into an anion. And once you have the anion, you've locked your EZ, right? So once you make that anion, you can no longer flip back and forth. So as the radical, so here, the methyl group is able to flip to be beside R2 or be beside R3, depending on which one's smaller, and it will go back and forth until it finds the most stable conformation. Once you turn that radical into an anion, you then lock that methyl group, and it can't flip back and forth anymore. So when it's the radical, at this stage, is when it decides if it's going to be E or Z, right? And then once you turn that radical into an anion, you've locked in that selectivity. You've locked in that EZ selectivity. Julia olefinations usually select for E. For E double bonds, it usually wants to put the two large groups on opposite sides. So at this point, then you add, like, there is a source of proton that will come in, usually in the workup, and that will lock your conformation. So there's a few examples of this that I have that are just kind of like basic Julia olefinations. So I specified this is the classic Julia olefination, which is kind of like a 3-step procedure: addition, add the acid chloride, then do your reduction. And then there's another version of this that kind of does everything in a single step. But for the classic Julia, right, the people have started varying the aromatic group. I have phenyl as kind of our stock example, but as you change the aromatic group, you change let's go back here, sure. Right, so you have the aromatic group here, and as that group changes, that changes some of the reactivity of the molecule, right, of the reagent. So here they use this imidazole variant, use HMDS, sodium HMDS, and a protonate. They add, and then here they don't actually add the acid chloride. They're able to just do the reduction and remove this OH, and they get a 5-to-1 ratio favoring the E, so the trans in this case double bond, in good yield. Here, I've kind of fast forwarded to where they put in the acetate already. So you can just use samarium iodide and HMPA, and that gives you a 1-to-1 ratio of E to Z, right? But if you make the double bond first, like the mechanism I had walked you through, then you do your reduction, and samarium iodide is the reductant. This other stuff's just solvent and a little bit of additive. The DMPU helps grab the samarium. Then you get the E only double bond. So the conditions here will vary the result. But if you need an E double bond, a Julia olefination is a good way that can just give you a straightforward E double bond. It can be used in, like, these are pretty simple examples. We can use it in slightly more complicated structures. So here, they've deprotonated their cell phone. They have their organometallic that adds, and then they add acetic anhydride. So instead of an acid chloride here, they add the anhydride, and they get their cell phone and their acetate, and then they use sodium, mercury, and methanol. So there's no base added here. So what's happening is when you mix methanol with sodium metal, you make sodium methoxide and hydrogen gas. So I'm sure somewhere there's someone in Gen Chem wants me to put some coefficients on that. Right? So you make your base in situ. You make your base in solution. All right, so the base, you're not adding an external base. The fact that you're mixing sodium metal with methanol just makes a base on its own. So this reaction is relatively slow compared to if you add water to sodium. That makes sodium hydroxide, makes sodium hydroxide and, again, hydrogen gas. So, story time. When I was in grad school, I was on the 12th floor talking to a guy from another group, and his lab partner, one of his group mates, was the next lab over, and we just heard boom and saw this orange flash in the hallway. And we went in, and this guy named Butch had burnt all the hair off the back of his hand, and like up to his wrist, had just burned it all off. And what had happened was he was a responsible person. He used sodium to do a distillation to make sure his solvent was dry, and he tried to quench his still by adding methanol. Right? This is slow. It will not catch fire. And so he added the methanol and he went to lunch. And the methanol put basically a skin of sodium methoxide over his over his sodium metal. And then he was like, well, I'm going to add water because I'm done now. So he added water, and the water dissolved the sodium methoxide skin on his block of sodium metal. And then he had sodium metal in water. and I think you guys have all probably seen that like experiment somewhere on TV or on the internet where you throw sodium in water and it fizzes around and then catches fire. Well, he was holding the flask and the sodium metal caught fire because it makes hydrogen gas and the reaction is exothermic, so it lights the hydrogen gas it makes on fire and basically shot like a foot long flame out of his flask that he was holding and just burnt all the hair off his arm. So his lab smelled horrifically like burnt hair. See what you're missing by me teaching advanced organic? There's going to be no sodium fires this year. Sorry. I know you're looking forward to it. You're like, I hate the hair on my arms. I want to burn them all off. I'm going to take advanced organic to make that happen. Right. So yeah, you're just making your base in the reaction. So then there is a one pot Julia olefination where instead of having to do all of this stuff where you like turn your alcohol into an acetate and then do the and then add a reductant. It just happens all in one step. And the thing that allows that to happen is you use this particular aromatic ring instead of phenyl, right? You use this and in one step, you will just make your double bond, plus you will make this as a byproduct. So the first step is exactly what we had seen before. Right, so you have your big aromatic group. This benzothiazole is the name of the aromatic group. Oops, the aromatic ring. So you add base to this, and you're just going to remove that hydrogen, just like you did before. Right, and then you're going to add that to an aldehyde. Same old, same old. Right, so this is exactly the same. So you're going to end up with something that looks like this. This will put an R1 here. Sorry, R1, R1. There we go. Sorry, I'll give you a second. Double bonds here. So I get to this intermediate. And then a rearrangement occurs called a Smiles rearrangement. So if we count 1, 2, 3, 4, 5. So from that negatively charged oxygen to the carbon that your sulfur is on is 5 atoms. So we're going to do try to remember here, an nucleophilic aromatic substitution. There we go. Where we're going to add a nucleophile. We're going to add that O minus to the carbon that has the sulfur on it, right? So if you remember nucleophilic aromatic substitution, from organic 2, right? You usually have some X group and then some electron withdrawing group, and you have a nucleophile, and the nucleophile wants to add itself to the carbon that has the X group. Pushes the electrons onto the ring, and then those electrons come back down, kick out the X group as our leaving group, and we end up with electron withdrawing group and our nucleophiles on, plus we have our X minus. Well, here we don't, our electron withdrawing group that we need to like push electrons toward is our nitrogen. So what happens is this, the O minus adds to the carbon that has the sulfur on it. So the sulfur is pulling electrons away from that carbon, making that carbon positive, and then we push electrons up onto the nitrogen, right? And then we're going to get something that looks like, see if I can draw it, this. Have R1 and R2. All right, so we're going to break our aromaticity. And then these electrons are going to come back down, push electrons onto sulfur. Sulfur is going to push its electrons down to make the double bond, push electrons onto the oxygen. And then that's going to make this. So this is our byproduct. We're going to make SO2 as a gas, and then we're going to make our double bond. I guess I got lazy here. One of these is up, one of these is down. So they're going to be on opposite sides in the ring, so then they'll be on opposite sides in the final product. So far, so good? Oh, I'll point out now, you guys did it. I knew at one point during the semester I would be teaching to an empty room. That time was today. There's no one here. Cue Celine Dion. All by myself. Don't wanna teach all by myself anymore. Sorry, there's no one here to stop me from singing. This is what happens. This is what happens. You brought that on yourself. Okay. So here's some examples of the one pot. So here we have a tetrazole, which is filling the same role as the benzothiazole. So as a general rule, let's write this out. The more not the mole, the more heteroatoms in an aromatic ring, the more electron poor the ring is. It just becomes easier to add to, right? So the more oxygens and nitrogens and sulfurs you put in an aromatic ring, the more electron poor, the more positive that ring is going to kind of act, and the easier it is to add to. I always like to say, you can kind of think about it as the more heteroatoms that you put in a ring, it almost like that aromatic ring becomes less aromatic. It's just easier to add to. It's just not as stable, right? For one reason is that you have, when you add to it, right here, when I added to this ring, I had a place I had a nitrogen, I could put that lone pair, right? Nitrogen's a little bit more electronegative than carbon, so it can take that negative charge a little bit easier. And having the nitrogen and the sulfur, the ring's electron poor anyway, so it's easier to put a negative charge on that ring because that ring already is lacking electrons. So here they're using tetrazole, so a 5-membered ring that has 4 nitrogens in it. So that ring is really electron poor. So once you do your addition to your aldehyde, it's easy for that O- to add to the carbon that has a sulfur to it and do the Smiles rearrange it and make the double bond. Right, same thing here. Here it's a little more complicated structure, but you can take you do your addition, you add your LHMDS, you deprotonate this carbon, that adds to the aldehyde, O- then adds to the carbon that has the sulfur on it and does the Smiles rearrangement. So those are some Julia olefinations. And like I said, these are good ways to make trans double bonds. So if you need a trans double bond, a Julia olefination will almost exclusively give you a trans double bond. Next up, we have Peterson olefinations. So these involve the reaction of an alpha silyl anion with a carbonyl carbon. So right, so you have some silyl group that you can treat with base. Make an alpha silyl anion. And then that's able to add to a carbonyl compound. Maybe it's an R3 and R4 to kind of match my slides. R3 and R4, not 2 R3s. And then this will fall apart in the presence of acid or base to give you a double bond. So what's nice, I guess what's nice and what's kind of challenging about a Peterson olefination is that you will end up making a mixture of addition products, right? Where you're going to make a mixture of diastereomers. You're going to have the syn diastereomer where your groups are on the same side. You're going to have the anti-diastereomer where they're on opposite sides. And you can take each of those and turn them into a different product. So if you have here, like if you look at the structure, R2 and R3 are on the same side here, If I treat this with base, R2 and R3 stay on the same side. If I treat it with acid, R2 and R3 end up on opposite sides. Same thing where I take the other diastereomer where R2 and R4 are on the same side. With acid, I put them on opposite sides. With base, I put them on the same side. So you have to be able to separate your two diastereomers that you make when you do the addition, because each diastereomer is going to react differently to acid or base to give you your product. So you can always pick which double bond geometry you want, but you have to know what diastereomer of the addition product you have when you start to do the reaction. So the reason this works, the reason we get to choose between like acid and basic conditions giving two different products is because silicon is unique. Silicon does some different things. So under basic conditions, the fact that silicon really likes oxygen takes over. And so the oxophilic nature of silicon causes the oxygen to make a bond with silicon. Under acidic conditions, silicon is able to stabilize carbocations through an effect called hyperconjugation. And that makes it so you're able to do an elimination where you remove water under acidic conditions. So kind of depending on your conditions, the different properties of silicon take over. Let me show you this real quick. So I use the term just real nonchalantly, hyperconjugation. And this is the ability of sigma bond electrons to interact with, one second. With other orbitals, right? So hyperconjugation is your sigma bond electrons. So the electrons in your single bond are actually able to like interact with or have almost like resonance with other orbitals. It's most often seen, right, with these interacting with carbocations. So a carbon-silicon bond let me do it this way. A carbon-silicon bond, this bond right here, right, is able to donate some electron density right? So that the electrons in your carbon silicon bond is able to donate some electron density into the empty p orbital that makes up a carbocation. And it being able to donate that little bit of electron density into that p orbital stabilizes the carbocation. Right, so it's able to make that carbocation a little bit more stable and make it so it forms a little bit easier. This donation, this is the hyperconjugation. So this right here, this bond donating some of its electron density into the p orbital, this is hyperconjugation. So carbon-silicon bonds do this, carbon-tin bonds do this to a little bit of a lesser extent, but they're able to just make carbocations that are basically beta to the silicon a little bit more stable than they would otherwise be. All right, so what is the mechanism of a Peterson olefination? How does this work? How about we actually, no, whiteboard's here, cool. All right, so we're gonna have, it's gonna work off the slides a little bit here. We're gonna have our R groups on our silicon. We're gonna treat this with a base, usually something like LDA, N-butyllithium. To make our alpha siloanion. Now we have to do something to differentiate this carbon right here from the screen, from these carbons here. So in a lot of examples, R1 or R2 will be an electron withdrawing group to help make the carbon that you want to deprotonate more acidic, because you're able to deprotonate alpha silo groups pretty easily. So you have to do something to make sure that you don't deprotonate these groups that you just need to have on your silicon, so your silicon has enough bonds on it. But you don't deprotonate this. You need to differentiate this from this carbon, so you can deprotonate the hydrogen that you need to remove to do your reaction. So you'll put an electron withdrawing group on there to make this carbon more acidic, right? Sometimes you'll use sterics, right? No, go ahead. Oh, it might be my like lovely coastal internet. Okay, how far back are you? Like I can like give you a sec. Like here, I'll go back here. So there was this, right? So we deprotonate here, make the anion, we add, and we get this acid base, make double bond, right? And then what I had showed, if I can get the thing up, right? What I had talked about, yeah, it gave me the like your internet's unstable at the beginning, and then it was like fine. So if it's an issue, let me know. We can okay, so we can totally just blame Coastal's internet. That's fine. Right, is you get different diastereomers, and depending on if you treat with acid or base, you get different products. So you can take those two different diastereomers, and you can always get them to the same double bond, but you have to use two different conditions. So if you have a mixture of diastereomers, you have to separate the diastereomers, treat one with acid, one with base, and they'll get to the same product. Right. And then I went on my little like hyperconjugative sidetrack here. Right. Interact with carbocations. Ta-da. So, like I was saying, so R1 and R2, one of them is typically electron withdrawing, or in some other way stabilizes an anion, or the R group is sterically hindered. So in a lot of examples, they use like triisopropyl, right? Because it's really hard to get to those hydrogens if you have 3 isopropyl groups on your silicon. So basically you make this side really big, so it's hard for a reagent to get to one of those hydrogens. So then the only hydrogen left for it to react with is a hydrogen you want to have it removed. So you've got to differentiate these carbons on your silicon from the carbon that you want to react with on your silicon. All right, so then you add, like I said, then you're going to add this guy, our R3 silicon anion. All right, we're going to add this to our aldehyde or ketone. I'm actually going to draw not like an idiot. There we go. Right. Did I actually number correctly? There we go. So we're going to add that, do a 1,2 addition to that. And now we're going to get 2 what is it called? 2 diastereomers. So you're going to have the diastereomer where you have R2 and R4 on the same side. Man, my handwriting just like went in the dumpster right now. Where you're going to have the diastereomer where, R2 and R3 are on the same side. Right? So I get these 2 diastereomers. And then you're going to add some sort of, acid to this, H+, right, just to quench your reaction, to just get something you can isolate. So you're going to end up with, if I can do this right, R3 silicon, R2, R1, try to get this right, R4, yep, R4, R3, so H plus R3 silicon, 2, R1. Okay, so we're going to get these 2 guys here. Right? Now, to get them to the same product, right, one of these I have to treat with acid and one I have to treat with base. So to match the slide, to match slide 35, to match what I did there, we can say that we take this and we treat this structure with base. Right, so we take this, we treat it with base, and we're going to get back to our anion. Right, and then this anion is able to add to the silicon. I'm going to go over a slide. So you end up with something that looks like this. So it's R2, R1. R3, R4. Our silicon ends up with a negative charge because silicon can make 5 bonds, but we make the 8 complex a silicate complex. Now, silicon doesn't want to have a negative charge, but it can. So what ends up happening here is this will fall apart. These electrons come here. These electrons go up to the oxygen, and this makes our double bond. And this is kind of like another one of those concerted paracyclic reactions where since R2 and R3 are on the same side, they in the four-membered ring, there's no time for the structure to rotate at all. So R2 and R3 have to be on the same side of the product. So this is how, under basic conditions, we can get this product. Right, now the other diastereomer where R3 and R4 are switched, to get this same product, I have to do it under acidic conditions. So the other structure, right, looks like this. Right now I have R2 and R4 on the same side as the other diastereomer. To make this be the same double bond where I have R2 and R3 on the same side, I treat this with acid. So I add acid and I protonate my alcohol. So my alcohol gets protonated. And what happens is for that, to help push that oxygen off, to help stabilize that positive charge, right, we want to rotate around that single bond. We want to put the oxygen anti to this carbon silicon bond. So we want to put that oxygen on the opposite side of the molecule. So what ends up happening is when I rotate around that bond, so uh, I don't. I don't know how I can fix that. Like, so I know there's a little lag, but if there's a big lag, it's probably an internet issue. Like, you can just yell at me and I will stop. So this is where I was, and so we have our we have our double bond with 4 and 2 on the same side, and then to get the same thing when we have the other diastereomer where you can see here 2 and 4 are on the same side. I need to get, I know I want these two, I want this and this to be together, right? I have to do that under acidic conditions. So you protonate your alcohol, and you want to have your alcohol on the opposite side from your silicon group. So I've got to rotate around that single bond and put that oxygen down. And when I rotate around that single bond, that brings R3 to the same side as R2. So I'm going to have, I'm going to have green stuff apparently. I have R1, R2. I've rotated around. My water is down, pointing down. This is going to put R3, R4. So now R2 and R3 are both facing forward. They're both on the same side of the molecule. And now we're able to take and these electrons can come down and push the water molecule off the molecule, and then that's going to make our double bond. And since I rotate it around, now I have again R2 and R3 on the same side, R4 and R1 on the same side. So it doesn't matter which diastereomer you make, you can always get to either the E or the Z double bond based on what conditions you use to make that, to break down your alcohol structure. How is my wonderful whiteboard? Are we all caught up now? No one's saying no, so this is good. Okay. So I have a few examples we can go through of the Peterson. Slide over. So here, so like I said, we needed to, so here's your aldehyde. Here's the carbon you wanted to protonate. So we want to make sure we've differentiated our silicons, our carbons on our silicons. So here we use isopropyl. So you actually have two silicons, right? So I've got, you're just gonna show up and there's just gonna be like a structure drawn. It's gonna be great. Right, so if we look at this structure, right, if we draw it all out, which he did without changing the screen, good job him, right, you have the easiest hydrogen to get to is probably right here, right? All of these hydrogens here, they're all surrounded by a bunch of isopropyl groups, right? So all of these are harder to get to than this one. And this hydrogen here is beside this alkyne, which will help stabilize the anion that you generate. So a combination of having really big isopropyl groups all over your silicon, combined with this hydrogen being beside an alkyne, is going to make it so we are going to protonate this hydrogen and not any of the other hydrogens on the molecule. Right, so then that's going to lead to only this anion being formed. Oops. Right. So the first thing you have to be able to do in your Peterson olefinations, you have to make the right alpha siloanion, because all of these hydrogens, right? All of these hydrogens here. Let me do it up here. All hydrogens here, 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 this one, right? Because they're beside a silicon, they are slightly more acidic than they would be if they were just on a carbon chain. So those are all hydrogens that if you add like N-butyllithium to, that N-butyllithium could possibly take. But you've made this one slightly more acidic by putting it beside a triple bond, and you've made it slightly easier to get to because you got a whole bunch of isopropyl groups over on your silicon that are going to make it hard to get to those carbons, or to get to those hydrogens. So step one is make a reasonable anion, be able to make that anion and make it so you can select for it. Right? Now, in this reaction, right, they don't do I'm all alone. This is Advanced Organic. They abandoned me. That's right, I'm telling people you abandoned me. I feel like a baby just left at the fire department in a basket. Like, he'll be fine. It's a better life form without us. Right? So if you look at this, right, they do this only under basic conditions. They only have the reagent add, and they don't actually separate the diastereomers. So what this can tell you is that, one, they're doing this under basic conditions. So, and they don't ever use the acidic conditions. So that means the addition, adding to the aldehyde, is very selective. So we get a 6-to-1 mixture of E to Z in our reaction for the double bond, which means in the addition to the aldehyde, we must be getting about a 6-to-1 ratio of diastereomers for the addition. So what's happening here, or what you can infer, is that we have our aldehyde. I'm going to not draw out the whole ring because I don't hate myself. Right? Ring. When we add our aldehyde, when we add our silyl group to it, isopropyl 3, we're going to pretend that fits. Yeah. There we go. When we're adding these two things together, what we're getting out, right, is you're going to have your silicon, and then let's say this group is up with our alkyne, our silicon, and then the groups that go to the ring, right, we have 6 of this to basically 1 of the other diastereomer. We're like the ring group is back. So because the addition to the aldehyde is very selective for 1 diastereomer, it means we don't have to worry about separating out the diastereomers and doing 2 different reactions, because we can just rely on the fact that the reaction gives us the diastereomer that we want that leads to the product that we want. So I will finish this last slide up on whatever that day is, Thursday. I was hoping against hope, that I'd have more slides. So I've already started the next set of slides. I was hoping that I'd have to use it till next week, but I think this means I'm gonna have to spend like all night Wednesday making slides for you guys. So we actually have like most of a lecture for Thursday. But yeah, we'll finish this up. We'll finish like going through this example and this on whatever day. Right, we'll finish up this example, and because this is an interesting step, and this on Thursday, and then we'll finish the Tebbe reaction, and then we'll start on oxidation of olefins probably. So unless anyone has any questions, I think we're good. I've uploaded a reasonable number of them. I feel like I've updated the last 4 or 5, but I don't know if I have the first 2 readily available. But I have the last 5 are done and up. So they are all there. I will check to see if I can find the ones before. I think they're on here, but I just didn't end up putting them up. But I can try to put them up. So with that, I guess we're good. See you guys on Thursday. You too. See you, Caitlin.